And we're still talking about logs. We'll be talking about logs for a while. So, oh, there's someone at the door. Put that ID on. All right, so so anyway, we're going to be talking about logs for a while. So some of the stuff that as we talk about, it's going to be, stuff that we talked about the day before also, or whatever, because they're still logs. But because we know logs and exponentials are inverse functions, something we talked about a lot yesterday, the characteristics of their graphs will be inverse relationships as well. So here are some key characteristics of logs. We looked at this general form right here yesterday that included the A, even though we hadn't really graphed anything with an A yet. We're going to look at that today, along with some other transformations. It says B has to be greater than 0. So my base can't be 0 and my base can't be a negative number. Doesn't work that way. And then we know what our domain and range is for our parent function. This is what our parent function looks like. Okay, we need to be able to draw that sketch and know that picture in our head. And this is what it looks like when A is greater than 0 and B is greater than 1. So when A is greater than 0, A is just our vertical dilation, right? So it's just getting stretched or compressed, and that doesn't really change what our sketch looks like. If we're actually plotting real points, yes, but when we're just drawing that, it is what it is. So if A is less than 0, so if A is negative, then when I have a negative out front right here with these functions, that means it's a reflection, and it would be a reflection in x because it doesn't touch the x, right? So that's what this is here. This is just a reflection of that one in the x-axis. Or we could get the same graph, or when A is greater than 0 and B is between 0 and 1. So if I don't have a reflection, but my base, so the bases that we've been using, like yesterday we graphed log base 5, log base 2, log base 3. But if I have log base 1/2 or log base 1/3, then it has the same effect as if I had a reflection in the x-axis, okay? Kind of like if you think about what you know about exponentials. We know that this is exponential growth, right? And this is exponential decay. So this would be like 2 to the x, and this would be like 1/2 to the x, right? That sound familiar? That's how you know the growth and decay. Same thing. Here are bases. If it's a number greater than 1, looks like that left-hand picture. If it's between 0 and 1, it looks like the right-hand picture. Okay, so there's 2 different ways we could get there. Increasing and decreasing. So logarithmic functions, by their nature, are always increasing or always decreasing. They will never switch, so they have no relative or local extrema. That was true for exponentials as well. That's why that sounds familiar, like we already talked about it. They are always increasing or always decreasing, so I'm not going to have any max or mins. It's impossible because we don't have that change there. Same thing with concavity. They are always concave up or always concave down. They will never switch, so they have no points of inflection. Because remember, your point of inflection is where you change concavity. End behavior. In general form, as the input values of x increase without bound, that means we're going to infinity, right? The output values will increase or decrease without bound. Okay. Bless you. Since log functions have a restricted domain, they are vertically asymptotic. Okay? Fancy word again, like multiplicatively was yesterday. Vertically asymptotic. That means you have a vertical asymptote at x equals 0. Just sounds fancy. As a result, the left-end behavior will occur as x approaches 0 from the right. Now, these statements are based on that general form up there without any translations, and translations are one of the things we're going to look at today. And so then some of these don't hold true, but that's because it's not talking about with translations. All right, so then our end behavior limit statements. We read this as the limit as x approaches 0 from the right of the function. That's going to give me either positive or negative infinity, right? Because it's going to hit that asymptote. It's got to go in one direction. And then as x approaches in positive infinity, or just infinity is fine, then the answer will be positive or negative infinity. Right? Sound good? All right, so let's write some limit statements. So here, my left-hand limit statement, this would be the limit as x approaches 0 from where? The right, that's why we put that positive sign, of f of x. And as we approach 0 from the right, what does the function approach? Negative infinity. Good. Then my right-hand end behavior, that's the limit as x approaches infinity of f of x. What is that? Infinity. As x gets bigger and bigger and bigger, so does y. So that's infinity. Okay. We okay with that? All right. So here, now to get this function, I could either have reflected f of x, or it could be a totally different one and not have a reflection, and the base could be between 0 and 1, right? Nobody's asking me for the equations, but I want to make sure that you know how that works. So for my left-hand in behavior, it's going to be the limit as x approaches 0, again, from the right, of h of x. Now be very careful. I mean, this is something that I know myself when I'm up here. Sometimes I mess up on too, and you need to call me out on it. This is called h of x. I need to make sure I put h of x here and not f of x, because nobody's talking about f of x and b, right? So what is this answer here? Infinity. Good. And then my right-hand in behavior, the limit as x approaches infinity of h of x is equal to what? Negative infinity. Everybody okay with that? All right. So yesterday when we started talking about the parent function, we were really just looking at like log base 5 of x or log base 3. We weren't really talking about that number in front of there. And I know if I just have a plain old log that my parent function just pretty much looks like that. And what's this point right here? 1, 0? Yes. 1, 0. Now, this 2 here, what kind of transformation is that? Dilation. So that's a dilation. Is it a stretch or a compression? Stretch. But really here, if it was a stretch or a compression, does it really change what my little sketch is going to look like? No, it doesn't. So that's why this is part of the general form, because that 2, as long as it's positive, whatever the number is, yeah, it stretches it and compresses it, and obviously it's going to change what those points are on there. But when I'm just trying to get a general picture to write my limits, it doesn't really do anything to it. Okay? So my left hand, once again, will you go ahead and write these out? I think you can write these limits out. And it's been a minute since we wrote them, okay? Concept hopefully is still there 100%. I would say about 95% of you were good on how you were writing them, but there were a handful of people where when you wrote them out, it kind of looked like a hot mess. Now, when we write them, I mean, some of y'all maybe have super perfect handwriting, and when you write them, it might look like if somebody typed it. Oh, hang on. Okay, so what I was saying was, and when we write them, I'm not capable anyway of actually writing it exactly like it looks here, because the x, as x approaches infinity there, that's like a subscript, and it's kind of written smaller. Well, that's kind of hard to do when you're just writing, which is fine. The most important thing that you have to do is that these two things are stacked on top of each other right here, and then the g of x is next to it. Okay, so just make sure you're paying attention to how you're writing it, and it's not in some weird order of whatever. Okay, we good? All right, flip it over. So we're going to talk about the logarithmic function, and whether or not it's increasing or decreasing, and concave up or concave down. Okay, so is this function concave up or concave down? Up. Is it increasing or decreasing? Decreasing. Okay, notice I said is it, right? What is it that I'm referring to? The function, right? The graph. Okay, now we can also talk about the rate of change, yes? Okay, and that's where a lot of us got things mixed up, like is the function increasing or decreasing, and then is the rate of change increasing or decreasing? So we can look at this a couple of different ways. So first of all, let's look at it just, what does rate of change mean? Slope. Okay. So my pen right here, this is going to represent my slope. This is the negative slope, right? This is a positive slope. Yes? What is this? 0. Okay. This one's undefined. This one's 0. Okay. So as my slope goes along here, my slope, is this positive or negative? Negative. And it's getting closer and closer to 0, right? So is my slope increasing or decreasing? Increasing. My slope is negative, but it's getting closer to 0, which means the value has to be increasing. You with me on that? And I know that that was like a little brain twister for some people, just to kind of wrap your mind around that. So remember, we also have the fun chart. So let's write out the fun chart. So this, you remember your U and your N look weird because it's really about concavity, but it kind of looks like fun. Then up, down, and then this is slope, which is rate of change, but it's easier to write slope. And I am hesitant to abbreviate rate of change because I don't want you abbreviating it anywhere. Increasing, decreasing, positive, negative. Remember that? So if you have a hard time thinking about how the slope is sliding around and what is happening to it, you can look at it this way. This is concave up. Since it is concave up, my slope is increasing. My function is decreasing. Since my function is decreasing, my rate of change is negative. Okay? Does that make sense? It was concave up. That's why my slope is increasing. That's what makes an increasing slope, is concave up. And then if I asked you, is the slope positive or negative, which you could do this, you can see that it's negative, but it's also negative because the function itself is decreasing. Okay? So you've got that chart there to pull things off of. If you can figure out the function, it can tell you about the rate of change. Okay? We good? All right, so let's look at B. Is the function concave up or concave down? Concave down. What does that tell you about the rate of change? It is decreasing. Is the function increasing or decreasing? Increasing. What does that tell you about the rate of change? It's positive. Okay? Make sense? That fun chart is important. Okay. So now let's look at C. They gave us an equation. They didn't give us a graph. We're going to sketch one because I think that that's very important here. If I look just at this part, if I ignore the negative, okay? If I ignore the negative and I just think of 4 log base, whatever, because I marked it out, of x, it's going to look pretty much like this, right? But then that negative is going to be a reflection in what? X. So if I take this and I reflect it in the x-axis, it's going to look something like that. So concavity, what is it? Up. What does that tell you about the rate of change? It's increasing. Is the function increasing or decreasing? Decreasing. What does that tell you about the rate of change? It's negative. Okay, so more charts. We love charts. Tables, whatever you want to call them. So we have selected values of several logarithmic functions as shown in the tables below. For each table, we're going to find the value of the constant k. Now, here's something important here. It tells us these are logarithmic functions. That's good. Okay? That means we know that if our y values are equally spaced, which in this case, they are, right? We're just adding 1 each time. Then our x values should change multiplicatively. What are these being multiplied by? 2. Okay? Right? We basically did that yesterday. There just wasn't a missing k there. So if that's the case, what does k equal? 4. So then I'm going to look at the next one. I'm first going to look to see that my y values are equally spaced, because if they're not, then I can't just go and figure out what's being multiplied on the left. They are. We're adding 5 each time. What are the x's being multiplied by? 3. So then what is k? 2. So we don't have to get crazy complicated with k, but they're not always going to be all that obvious and that easy. Hence the next one. When I look at this one, I am adding a -10 each time. Because remember, we talk about it being adding stuff and multiplying stuff. We don't talk about division and subtraction with these. Now, That means, and now yesterday we were trying to figure out, is it logarithmic, is it exponential, or is it neither? We're not trying to figure out what it is. They flat out told me they are log functions. So I know that these change multiplicatively somehow. Now, it's not some crazy decimal or anything, because that's not going to work, because 4/5 is not the same thing. I'm sorry, 5/4 is not the same thing as 7/5. But there's a transformation in here, okay? There's a translation, so we have to add or subtract something. So we could look at it from going from y to x, but if you just look at your x's, like once we got here, we didn't care how 5 got us 6. We weren't trying to find the equation. We're just like, oh, we multiply by 3. Like, how do I get from this one to this one? So we want to figure out, using some multiplication and either addition or subtraction, how do I get from here to here? And then from here to here. And they have to be the same pattern, right? So we could subtract. One of the things we did with the exponentials is we subtracted first. So I would do 5 minus 4 gives me 1. 7 minus 5 gives me 2. And then we might have to subtract again. But I don't have enough to do that because that k is in the way, right? So instead, on this one, I would suggest some trial and error. Like, what could you multiply 4 by and then add or subtract something to get 5? And then would that exact same thing work to go from 5 to 7? Times 2 minus 3. So if I take 4, multiply by 2, I get 8. Subtract 3, I get 5. Take 5, multiply by 2, I get 10. Subtract 3, I get 7. That sounds good, right? So I'm going to take 7, multiply it by 2, I get 14. Subtract 3, what do we think k is? 11. And then we want to make sure that it works. 11 times 2 is 22, minus 3 gives you 19. Okay. I don't think you're going to have many of these. That's why I think trial and error on that is probably the best. Really, because I don't think they're going to be so complicated you can't figure them out quickly. Alrighty. Then this last one. Here, I am adding 7 each time, which means something is happening multiplicatively over here. To get from one to another, am I multiplying by a constant like 3 or 2 or something like that? I'm not, right? I'm going to have to be multiplying by e in some way. Now, the fact that this is e doesn't make it crazy hard, and the fact that e is about 2.7 helps me exactly none, okay? So I'm going to have to multiply e to the negative 2 power by something, and it's going to have to equal e, which is really e to the first. So the only thing I can multiply it by, where another number, or something doesn't show up, is e to some power. What is your rule when you multiply two things with the same base? What do you do with the exponents? You add them. So what does this exponent have to be? 3. Because when I multiply e to the negative 2 times e to the third, I add those exponents and I get e to the first. Boom. So if I take e to the first and multiply it by e to the third, what do I get? E to the fourth. So I think k is e to the fourth. Well, let's make sure it still works. E to the fourth times e cubed, e to the seventh. E to the seventh times e cubed, e to the 10th. Okay? We good with that? So that's not really so much about, oh, I don't understand e. That's more about exponent rules. Okay? We good? Alrighty, good job. Alright, so now we're going to find, we've got some more of these, but these have some transformations in them. We're going to find the domain and range and write our limit statements. So we're going to sketch something first. So when I sketch this, that's just this. Would you agree with that? Okay. And one thing I don't put on my sketch, but I can't lose sight of the fact that it exists, is that there is an asymptote right here, right? No need to, sketch it in every single time unless you feel like you need to. Just remember that there is one there. All right, so my domain, where do I start? 0, and I go to infinity, and then my range, negative infinity to infinity. My left limit will be the limit as x approaches 0 from the right of f of x. What does that equal? Negative infinity, good. And then the limit as x approaches infinity of f of x is infinity. Any questions? All right. So then we have this one. Well, and I'm going to do this in 2 steps. You don't have to, but I don't want to lose anybody, right? So I know I start off with something that looks like this. Then this negative is going to be a reflection in what? The x-axis. So then it looks like this, right? Just when I'm just doing that negative. And then this means what happens? To the right 3. Okay. So what is this point right here? 1, 0. Okay. And so if I move to the right 3, this really ends up at 4, right? And so I don't need that anymore. And then my asymptote, which was right here, where does it end up? At 3. Because the whole thing shifts over, right? The negative there does, the reflection does not affect the asymptote, but the shift does, okay? And then the reflection affects our limit statements, but it's not going to affect our domain and range. So my domain, where do I start? 3. So I'm going to start at 3, I go to infinity. My range is the same. So then I'm going to have the limit as x approaches what? 3 from the right. Good. 3 from the right of g of x, and that's equal to infinity. And then the limit as x approaches infinity of g of x is equal to negative infinity. Okay. What questions you got? Okie dokie. Domain and range of the next one. Now, when we look at transformations, when you look at something and it's written in this form, this does not move to the left 3. If you have a number in front of x, which is being multiplied, which will be our horizontal dilation, it has to be factored out of what's in there for us to do our transformations like we've been doing them. So first thing I need to do is rewrite this. H of x is equal to 8 times the log of 2, open my parentheses, times x plus what? What did the 3 have? I think I heard 3 halves. Okay. Because you divide each one of these by 2. And if you multiply it back, 2 times x is 2, and 2 times 3 halves is 3. All right, so now that it's factored out like that, now I can look at this. This is my horizontal dilation. This is my horizontal translation, okay? So when I go to graph my little parent function here, I've got the 8, I mean, that stretches it. Even the 2, that horizontal stretch and compression, that doesn't affect anything. The only thing that's going to affect my domain and range and my limit, or not the only thing that affects my limits, but my domain and range is going to be the shifts. So I shift where? Left 3 halves, right? So I end up with this right here, right? So where is that asymptote? Negative 3 halves, right? So because I shifted this, but remember this was at 1, it wasn't at 3, it wasn't at 0. So when I shift to the left 3 halves, this is now at negative 3 halves. So my domain starts at negative 3 halves, goes to infinity. My range is the same. My limits, see if you can get those written out. What questions you got? Good? Awesome. All right, grab your other sheet of paper. This is also going on 79. You have a question? Yes, you do. Ask me a question. Do I need to go back? Okay, back here? Okay. So what part is confusing you? The concavity or the slope or the what? The slope. Okay. So the slope, remember this is that we're talking about, we talked a lot about average rate of change, and then we talked some about instantaneous rate of change. And so at this point, the slope of the, well, that's bad, but the slope of the little tangent lines that go like this, right? Okay. So would you agree that the slope of each one of those lines is the slope negative? Yes. Okay. As x gets bigger and bigger and bigger, do you see how the slope itself, it's negative, but it's getting closer? Like if this was a parabola, it would be negative, and then it would get hit to 0, and then it would become positive, right? Now it's concave up, and it's not going to do that, but even though it's not going to become positive, the slope values of each one of these, if I get each one of these values, my numbers get bigger and bigger and bigger. They're still negative, but they're bigger numbers. Like if I had -2, and then -1, and then -1/2, and I'm getting closer and closer to 0, right? These numbers, even though that, visually might look like they're getting smaller, they're actually getting bigger. So that means that your slope is increasing. Your slope values are increasing. Okay. This is one reason why we have the fun chart. Because, right, the slope is increasing. This is the function. This is the function. That's why. Is that why you're confused? And honestly, that's one thing that was confusing people a lot, was the function is decreasing, but the slope is increasing. Right? The function is concave up. That's what tells me that the slope is increasing. That doesn't give me the answer to the second question. This is about the function. This is about f. Okay? And you will be asked, is the function increasing or decreasing? Great. Is the slope increasing or decreasing, or the rate of change? So this is one where we would say it is decreasing at an increasing rate. Right? Because the function is decreasing, the rate is increasing. Does that help? Okay, see? Everybody good? Anything else? Does that help? Okay, see? Helps more than just you. Thank you for asking. Okay. Okay, so we've got this graph of the log. Now, my suggestion to you on these is even if it's multiple choice or matching like this, still start by drawing the sketch. That needs to be your go-to before you look at graphs that are going to confuse you and make you question everything. This is just your basic graph, right? So, boop, it looks like that. Which one is that? C, right? Is that basically C? None of the rest of them kind of look like that? All right, so this is C. This one is kind of like that, except I have a reflection in which axis? Y. So that means it's going to look like that. Which one is that? A. All right, and then this one, we take the original one, and what does this reflect in? The x-axis, right? So it's going to look like this. Which one's that? B. Now, this one, I got two things going on. This base, this is 1/2, tells me that if that was the only thing that was different, we're going to ignore that negative for just a minute. If this was positive and that was 1/2, it's going to look like that, right? But then what does this negative do? Reflect in the y-axis, so it's going to look like that, which is D. So it might be helpful to kind of draw them in stages to make sure you flip them around the right way. We okay with that? Draw them every time, every time. Okay, so now, given these functions, we're going to determine the asymptotes and the end behaviors using our limit notation. So once again, we're going to draw a picture. What's the base of this log? 10. Has no bearing on the problem, but that's something we need to know, right? So I would take my normal log function, and it gets shifted which way? To the right one, which means it looks like this, and my asymptote is now right here, right? And I have a vertical asymptote at x equals 1. So I went from 0, moved it over to 1. Then I'm going to write my limit statement. The limit as x approaches 1 from the right of y, because it's not called f of x, it's just called y. That's fine. It's defined. That's equal to negative infinity. And then the limit as x approaches infinity of y is equal to infinity. Everybody okay with that? I know we're writing the limits a lot, but I needed you to remember how to do them. Okay, so here, which way does this get shifted? Left, too. So it looks like that. Here's my asymptote. So my vertical asymptote here is at x equals what? Negative 2, exactly. So then we're going to write the limit as x approaches negative 2 from the right of y is equal to negative infinity, and the limit as x approaches negative 2, approaches infinity of y equals infinity. Everybody okay with that? Any questions? Okay, so C is not written in the order that we normally see it in, but we should be able to still figure out what's going on. What kind of transformation was that 2 do? It's not being multiplied, so it's not a dilation. This is a translation. Usually we see it at the end. Couldn't I have negative log of this plus 2 at the end? Yeah, so this is a vertical translation, right? So I'd go up 2. What does this negative do? Yeah, it's a reflection in which axis? X. And then this means I go in which direction? Left. 4. Okay. So I would take my original log. I'm going to shift it up 2. Does that really affect my sketch? No, because my sketch is pretty sketchy anyway. That negative is a reflection in the x-axis, but then I move to the left 4, so it's going to look like this. Here is that. So my vertical asymptote is at x equals what? Negative 4. So the 2, although it is important for the graph, obviously if I was going to graph it accurately, it doesn't really change anything for my limits. Okay? It's the shifting left and right that does, not the up and down. And so then I'm going to have the limit as x approaches negative 4 from the right of y equals infinity. And the limit as x approaches infinity of y equals negative infinity. Okay. Any questions about that? Okay, we're going to change D a little bit because I intended on doing something that clearly I did not do. So instead of this being x, it's going to be negative x. Okay. So when I go to draw my sketch, does that negative 3 really do anything to my sketch? No, because it just shifts it down and it's not going to affect anything. But that negative on the x, that's a reflection in what? In the y-axis, so that means my function looks like this, right? When I did that, did my asymptote move? No, so it's right here. So my vertical asymptote is at x equals 0 still. Now, when I go to write my left-hand limit, the left-hand side of my graph is heading to what? To the left, yes. Towards negative infinity. Good. So the limit as x approaches negative infinity of y equals infinity. My right-hand limit, that would be the limit as x approaches 0 from what? The left of y equals negative infinity. What questions you got? Explain the limits. Well, here, up here, I had to, when I'm going to the left, I'm approaching an asymptote. When I'm going to the left here, my x's will approach negative infinity. And that's why I'm going up to infinity. Because it got flipped around, when I go to the right, I hit that asymptote. So when I approach the right, I'm not approaching infinity, I'm approaching 0, but I'm coming from the left-hand side. Okay? Anything else? Yes, ma'am. Yes, it affects the domain also. Is that what you're asking me? No, I'm not sure what you're asking me. Yes. Okay. And so, yes. So, yes, absolutely. The asymptote, yes. And here, let's just write it because you asked that question, and I know you weren't asking about this one. But for this one, the domain, I start out at negative infinity, and I go to 0. So, yes, that here, my domain would go from negative 2 to infinity. But you want to make sure you know which side of the asymptote you're on how to draw it. But yes, absolutely. Good question. Anything else? Okie dokie. Now on this one here, we're going to answer a question that's not being asked because I think we need to. We are going to write down our fun chart again. And because I don't have a whole lot of room, I'm going to put S for slope. Oh, but let me do it correctly. Good Lord. Increasing, decreasing, positive, negative. Okay. So without graphing it, because it does say we can graph it, and we will, I should be able to look at this and tell, is my function increasing or decreasing? Increasing, right? Because you can see your function values, they're increasing, right? So I can say f is increasing. And then I'm going to say, therefore, now if the function is increasing, what does that tell you about the rate of change? Good. If it's increasing, the rate of change is positive. Now, whether or not this is concave up or concave down, we can graph it, so let's go ahead and graph it. I'm going to go to a little bit more than 1, and negative 2.8620. 1. That's the best I can do, so it's going to look something like that. So is this concave up or concave down? Down. So then I can say F is concave down. Therefore, the rate of change is what? If I'm concave down, rate of change is decreasing. Okay? Straight from that chart. And then domain, which is what it asked me for. Where do I start? 0 and go to infinity. What questions you got? All right, you work on B while I hand out your assignment, and then we'll do it together. Who are we missing right here? See, y'all are missing Gavin, right? Who are y'all missing? Yeah, I know it's these two. Shame on y'all for not knowing their names. We're gonna play the name game on Monday. Mm-hmm. Oh, I'm missing Shane, right? Jesus, I can't graph. Okay, so negative. Whatever, close enough. So G is concave up. Okay, so did you get that the rate of change is negative at first? Yes. And then since g is concave up, rate of change is what? Increasing. Good. Now, you do have to kind of assume some stuff to get the domain, and I understand that, but where would it make sense for the asymptote to be? Yeah, at -2. So we're going to go from -2 to infinity. We good on that? What questions you got? You feel good about limits?